we are adding yet one battery superstar to this portfolio, and this is Professor Stefano Passerini. He is now professor at La Sapienza in Rome, but this is a very recent position for him because a lot of us know him from him being director of the Helmholtz Institute in Ulm for many years in Germany. His research is focused on basic understanding and development of materials, both for batteries, but also for supercaps. And he's really a true pioneer when it comes to research on ionic liquids and on sodium-ion batteries, where he recently hosted one of the major conferences in this area. Stefano has published more than 700 research papers and has an H-index of more than 100, which is truly impressive. We also know him as the editor-in-chief for Journal of Power Sources. He has handled many of our manuscripts, and he is a fellow of both the ISE and the ECS, the Electrochemical Societies, and he is a member of the Leopoldina German Academy of Science. We are very happy to have him here, and now it's time for him to share some of his knowledge with us. Thank you.
Well, thank you, Daniel, for the very nice introduction. Let me share my screen now, and also for the invitation to give this presentation. Thanks to you and Christina. Today, however, I'm not going to talk much about batteries, I have to say, but more about a new field, let's say, of research I entered a couple of years ago, actually, together with a group located here in Italy. And it's more dealing with the energy transition. So more than conventional batteries, it's more how do we replace the oil in the future if we really want to decarbonize Europe. And everything actually starts from no, this is not the right way. Okay, everything started, let's say I started to think about this a few years ago when there was this announcement of the European Union that wants to decarbonize by 2050, which is definitely a tough target to reach. Okay, and I started to consider, okay, how do we use fossil fuels right now? And if you look at this graph on the bottom left, you see that it's about a third each between transportation, residential, and industry. Okay, plus there are some other consumption which are definitely minor. And obviously there is a need of addressing all of these fields. Definitely, we need to secure the energy needs for transportation, residential, and industry. I mean, there is no doubt on this. And this problem actually has been a little bit stressed this year due to the unfortunate Ukraine-Russia crisis, which in a sense has been a kind of push on this subject, okay? Because if we don't get gas from Russia, then it's going to be a problem. And this is what we are actually, what we want to do by the year 2050, not to use gas and oil anymore. Okay, batteries for sure have done a lot. I mean, I'm not going to go through the importance of batteries, but definitely they are extremely useful, especially lithium-ion batteries, but there will be other chemistries coming up soon, especially for, electric vehicles, also for residential. In terms of day and night cycle, I have here in Rome, in my house, I have a wonderful 12 kilowatt-hour battery that allows me to store energy during the day and then use it at night. But definitely the field in which there has been this the strongest push on batteries, it's transportation, okay? And this has been driven by these calculations, which you can find from many different sources. But it's clear that the energy storage in batteries is way more efficient than in hydrogen and liquid fuels. So for transportation, we definitely need to go toward electric vehicles. And this is what is happening already. Because if it is true that we can collect a lot of renewable energies, it's never that good to waste a lot of energy in the intermediate steps to the utilization. So this great advantage in the battery-powered vehicles, it's reflected actually by finally electric vehicles being deployed on the market and made available. And you see here kind of forecast on what is going to be the future of electric vehicles worldwide. And you see that in the 2022, China already reached 20% of electric battery-powered vehicles. Europe is around 15% overall. US is a little bit behind. But there is also this estimation that the European Union, and we definitely see it, I mean, there are continuously announcements from the big European car makers to go electric with batteries, that by the year 2026, or anyway, by 2030, the European Union plus the EFTA countries and the UK are supposed to have more than 70% of cars actually being powered by batteries. So even more than China, but these are forecasts. But let's take it as valid, okay? Nonetheless, and although electric vehicles have been developing, I mean, the effect on the CO2 emission of these EV is only up to the 2021. It's mostly, see, I have to admit, in the Scandinavian countries, and especially in Norway. You see this very nice data offered by the Association of European Car Makers, showing that in Norway, for example, there has been a almost 28% reduction of CO2 generation in between 2020 and 2021. Germany is kind of flat, but most of the other countries actually in Europe have increased the CO2 generation due to transportation. But let's see, I mean, the 2022 report was not available, so I could not show it, but I hope that it's already showing some good signs also in other countries than the Scandinavian, which are, as usual. Decarbonizing Europe, I mean, with the progression we had on LEABs and maybe we will have on SEABs, for sure, we will be able to solve the problem of transportation. So we won't need to generate CO2 or to use fossil fuels for transportation anymore. It's just taking the time for all vehicles to be replaced by EV. Definitely it helps, and you see the green and red line, I mean, on the residential, but excluding heating, I would say that I made this slide when I was in Germany, okay? So I was focusing on heating, but actually, now that I'm in Italy, I will care more about cooling in summer. And definitely there is no help coming from lithium-ion batteries for the large energy consumption of industry yet, okay? So for this, we need to come up with some new ideas. I mean, and the problem is not energy, okay? I mean, the primary energy needs of Europe in 2018, and for Italy, we got the value in 2019. It's about, let's talk about Europe, 21,000 terawatt hour for the whole year, okay, for the whole Europe, including also the UK. And if we look at the area of photovoltaic system, we need to meet these energy needs. This is not that much, actually, okay? So if we cover the entire Sicily, Sardinia, and half of Puglia, which are two islands and one southern region of Italy, in theory, we can generate all the energy we need for the entire Europe, okay? In terms of photovoltaic panels, maybe you can see this black stripe here on the European map, and you see this is the equivalent of area we need to cover with the present photovoltaic panels, so not even the most advanced, to generate all the energy needed by the whole Europe, including the Scandinavian countries, which unfortunately are out of these graph. So that's definitely not much. Okay, for Italy, it's even less. For Italy, it's only 6,000 square kilometers, the area that we need to cover. And if you consider that in Italy, there are about 20,000 square kilometers of urbanized territory, I mean, buildings, railways, roads, motorways. So it's clear that, I mean, there is plenty of space to install these photovoltaic panels to generate all the energy that is needed in Europe. The real problem, it is actually more, so, I mean, we should, definitely we want to install this panel to gather more solar energy. We definitely want to maximize as much as possible the wind energy too. But at the very end, what we really need now is more energy storage, okay? And actually, it is the seasonal annual kind of energy storage which we are looking for, because we need to be prepared for the next winter. And this is actually right now the key for renewable energy independence, so that we don't really need to buy fuels from other countries, and also obviously the decarbonization. So some time ago, there was a meeting I organized in Ulm, Electrochemistry, and there was a scientist visiting from Canada, a German scientist, but he's presently working in Canada, and he showed this sentence, okay, which is from Oswald. I also use the English translation. The path leading to the solution of the most difficult of all technological questions, the delivery of cheap energy, must be discovered by electrochemistry. I think this guy was really a visionary person, because, I mean, this was more than 100 years ago, okay? But I always been thinking about this sentence, and then I started to think about, okay, and this was, let's say, the spark that made me thinking about how to solve the energy problems or the decarbonization issues of Europe, okay? So, as I mentioned before, we have plenty of sun available, especially in the southern part of Europe. And we don't really need to store the whole energy we need in 1 year. I mean, to be safe, this is an estimation we have made. To be safe for the whole Europe, we only need to store about 4,000 terawatt hour. And for Italy, it's even less. It's about for the seasonal storage, okay? And for Italy, it's about 1/10. Italy consumes more or less 1/10 of the overall energy in Europe. And the same is also for the daily storage. I mean, most of the energy in the future, the renewable energy, will come from photovoltaics. So definitely we will have to cover the night and day cycle with some kind of storage. And there the need is only about 30 terawatt hour per day. Okay. And then I was thinking at that time, and again, it's nothing new, because this approach was already proposed in the 70s, in last century, when there was the first oil crisis, okay, to use metals to store energy. I mean, there are a lot of metals that are supposed to be energy consuming, so it takes a lot of energy to produce them. But the reason of this is that they are actually storing a lot of energy inside, okay? And this is what I usually define as reactive metals. So these are all the metals that can spontaneously react with oxygen and then free a lot of energy, okay? And as we will see later, I mean, the most promising are obviously aluminum, very light, magnesium, very light to electrons, calcium a little bit less, silicon, sodium, and so on. And the other great advantage is that these metals are also rather abundant. So if we look at this fancy map, it is very clear that, I mean, sodium, magnesium, silicon, aluminum, calcium, and also other are very abundant. So, and they are mostly available everywhere. I mean, aluminum and sodium, for example, are available everywhere. Okay. And then we started to elaborate on this idea. And we came up doing a little bit of analysis. This was already a work together with the group in Perugia, led by Professor Barelli. And here is the most important graph, okay? So the red dots in the center are the beast we want to beat. So we want to get rid of natural gas, liquid and diesel, gasoline, I mean, all fossil fuel, okay? The approach which we are taking now at the European, but also at national levels, it's hydrogen. So hydrogen seems to be, you know, let's say, the solution for everything. But if you look at this graph, this is very important, okay? I mean, on the x-axis, you have the gravimetric energy density, which for hydrogen is just unbeatable. I mean, there is nothing better than hydrogen. But if you look at the volumetric energy density, that is what is important, especially if you want to do the seasonal energy storage, you need a lot of energy. We were talking about 4,000 terawatt-hour for Europe, okay? Then the volumetric energy density starts to be also important, okay? And metals, even the most reactive like sodium, are always much easier to store than a gas, okay? Liquefied gas, especially liquid hydrogen, I mean, you need very low temperatures, okay? So metals in general offer these advantages: high volumetric density, high reactivity. Usually you can select metals that are not considered to be critical, okay? They can generate energy without producing CO2 because these are metals, okay? Most of them are not toxic. I mean, you can, again, exclude those that are toxic. So those that we are considering here, aluminum, magnesium, calcium, sodium, even lithium, a little bit less, but they are definitely important in our biological life, okay? So they are not that toxic at all. They should be local available and easy to transport, and also easy to recycle, okay? So aluminum is definitely an amazing case, okay? And this is the demonstration here. So if you consider 1 terawatt-hour of energy, you can store it in a volume of aluminum, which is 1/10 of the volume you need of liquid hydrogen, okay? The point is that you can store aluminum everywhere. I mean, you can abandon it in your garden if you have it. There is no problem with it, okay? While obviously to store hydrogen, both liquefied or compressed, is not that easy, and definitely it's can be a problem. So another calculation here. These are examples which are really important, okay? So if you store 1 cubic meter of aluminum, this is actually the primary energy consumption of a household, a big house with a garden and so on per year in Germany, okay? And 1 cubic meter of aluminum is not much. It's smaller than my desk here, okay? But even more important is the example on the right, that 1 terawatt-hour, which is the consumption, the energy consumption of a small city, can be stored under 1 soccer field if you put 7 meters of aluminum. And then you have energy storage for 1 year for this. And every small village in Europe, I think, has a soccer field, right? Only in Germany, there are more than 30,000 soccer societies. And I'm sure that they have at least 1 soccer field each. So this would account on 30,000 terawatt-hour stored only in Germany, okay? To give you an idea of the scale, because this is very important. Okay, sticking with aluminum, there are practically 2 possibilities to get the energy back from aluminum, and one is the thermodynamic conversion. Practically, you burn aluminum not with oxygen, but with water. And I'm going to show you why this is preferred, because practically 50% of the energy is generated as heat, which then can be transformed, for example, in electricity using a turbine, and 50% of this energy is delivered as hydrogen, which can be used again to produce electricity, but can also be used for other applications, for example, the chemical industry. I mean, we know that right now, European chemical industry is a big consumer of hydrogen, And usually this hydrogen is produced starting from methane, okay? And then obviously more interesting for me, because I am an electrochemist, there is also the electrochemical conversion. So use of aluminum in primary batteries with the direct conversion of aluminum into aluminum or aluminum hydroxide and electricity. Frankly speaking, although I am an electrochemist, the thermodynamic conversion is easier to approach, okay? And this work was done in collaboration, I mentioned already before, with Professor Brandell of the University of Perugia. So we went quite farther with this, up to the point that we actually designed a multi-service, made a multi-service case for electric mobility and energy storage services. So a whole concept of storing energy via aluminum and then producing hydrogen and electricity in a refilling electric vehicle refilling station, and the excess electricity obviously can be added to the grid. And this is based on a 4 mega. I mean, the charging station is a 4 megawatt power charging station, completely based on aluminum, which is fully recycled because the product of the aluminum combustion with water is actually aluminum oxide. Okay, we did some, the University of Perugia, they are engineers, they did some calculation. And if you look at the round trip efficiency on this cycle based on the wet combustion of aluminum, it's about 35.6%, which is in the same range, if not better, than hydrogen, as well as many other energy carriers which are being considered. But this obviously includes also the energy efficiency of the aluminum production. So this is the real round trip efficiency for the whole cycle. And definitely it shows very promising, because we still lose about 2/3 of the energy we capture, but the aluminum industry is already existing. So we don't need to invent anything there. They are already progressing toward CO2-free production of aluminum. We just need to develop the aluminum wet combustion apparatus, which does not exist yet at the industrial level. Everything else is available. Turbines, these kind of things are completely available. So in this field, we also did some preliminary tests. It's not only paperwork, there have been also preliminary tests, and we developed a small, in Perugia, a small bench to do these tests. And we start with aluminum, we inject water vapor in this aluminum powder, and then we actually check the amount of hydrogen which is produced and heat. And what we have seen is that at about 850, 900 degrees centigrade, we can get a pretty good conversion of aluminum into hydrogen, okay, with yields that are on this preliminary system, yields that are above 70% of the conversion, okay, which is pretty good. But as I said, we are also electrochemists, so we also want to study the electrochemical conversion, and this is something that is actually being done now still at HIU in Germany. And there are also other people working. I mean, worldwide, it's not only us. I mean, there has been a lot of study on the conversion of aluminum into, aluminum, the electrochemical conversion of aluminum into electricity. And there are some results showing that air or oxygen can be used, and the use of oxygen actually becomes interesting, so that only at very high current densities, while air can be normally used. And we actually did these tests. Also, I cannot show much on this because it's unpublished yet, and you told me that you wanted to record this presentation. But I can just show that, for example, we also confirmed that the use of air or oxygen is not that important when currents below 100 milliampere per square centimeter, milliampere per square centimeter are used. But on the other end, we also have found that very high efficiency, both Coulombic, but also energy efficiency out of the electrochemical conversion can only be obtained using super pure aluminum. The technical grade aluminum, let's say that this is the aluminum which is used for cables. So the cheapest one, 99.8% purity, so it's not too bad, actually has very poor, offer very poor Coulombic efficiency and energy efficiency performance, which are not even closer to those obtained with the thermodynamical process. And there, the main problem has been identified in the iron, which is always frequently present in aluminum, which is actually acting as a catalyst for the hydrogen evolution, which is something we don't really want if we want to transform or go directly for aluminum to electricity transformation. The second kind of metals we have been investigating, actually I started with this metal, is sodium. Sodium is definitely interesting because seawater contains a lot of sodium and is the most abundant chemicals on Earth and is widely available everywhere, okay? And 1 kilogram of seawater contains about 10 grams of sodium. So this is 1%. Which, there is no other mining activity that can be competitive with the extraction of sodium from seawater, okay? That's extremely easy. And the idea there is to practically produce energy with renewable and then use a seawater battery to actually store energy and deliver it when it's needed, okay? How does it work? Definitely, you don't want to have sodium metal and seawater in direct touch. So these kind of cells usually employ a solid-state electrolyte, which separate the negative and positive compartments, okay? But all the components of these cells, if you want, you can have a look to the published papers, make use of non-critical materials and offer pretty high round-trip efficiency, more than 70%. So the concept here, the electrochemistry of the sodium seawater battery is rather easy. I mean, during charge, sodium chloride, which is dissolved in water, is transformed into sodium and chlorine, okay? Or selecting the appropriate catalyst on the aqueous side, oxygen can be produced, but chlorine is a precious chemical, so it is preferred, okay? And during discharge, the process is reversed, and it is actually producing sodium hydroxide in discharge, deliver energy, electric energy, but it is also generating sodium hydroxide, as I mentioned before, which one might think it's bad, but actually is extremely good because we can use it to kind of solve one of the problem of CO2, which we have been accumulating in the atmosphere, because sodium hydroxide is an excellent trapping material for CO2, okay? Forming sodium carbonate, which can then be moved away. So obviously in such a cell, the energy stored is only proportional to the amount of sodium stored. Okay, so we need to maximize the amount of sodium which is stored in the negative compartment. And as I said before, we have this byproduct on the positive electrode, which are everything except bad, because chlorine is a precious chemical, as I mentioned before. The other great byproduct is actually the desalinized water, which is generated during charge, okay? Because sodium chloride is removed, and sodium chloride is about 80% or 90% of the salt present in seawater, okay? And then sodium hydroxide for the CO2 trapping I described earlier. So the other great advantage is that seawater, as I mentioned, contains plenty of sodium, so there is no need to have sodium in the cell when it's fabricated. And in a sense, this is actually going in parallel with the concept of anode-less sodium, but also lithium metal batteries, where obviously to maximize the energy, we want to leave the intercalation anode, and we want to go to the metals, either sodium or lithium. But this is still something to be achieved, okay? So the advantage is obviously that there is no excess sodium at all in a seawater battery, because we have the sodium is in the seawater, okay? Easy fabrication and also possibly higher energy, okay? So in order to develop this sodium anode-less sodium seawater batteries, we needed to favor the sodium metal deposition on the current collector, okay? Doing this directly from the nasicon, so from the inorganic solid state electrolyte, is not an easy issue, actually, okay? Because this leads to degradation of nasicon. And then we started to think about, and initially we investigated the use of ionic liquids, and we demonstrated that actually ionic liquids can reduce the degradation of the nasicon electrolyte induced by the plating of sodium metal. And then we went a little bit back, because we have been working for many years on on PEO-based electrolyte for lithium batteries, including ionic liquids. So we just copy-pasted the recipe of preparing this polymer electrolyte, but we replaced the lithium TFSI or pyrrolidinium TFSI ionic liquid with the sodium FSI salt and the pyrrolidinium FSI ionic liquid. We actually did not even investigate other compositions than those we investigated for the lithium-based batteries, okay? So you see what we get on the right is a polymer which is completely amorphous. It doesn't leak anything. You can put it in a TGA and you won't see anything moving out before the decomposition actually of the polymer electrolyte or the polymer. Surprisingly, the first compound to decompose is not the ionic liquid here, it's not the sodium salt, but it's the polymer, the PEO polymer, okay? And what was surprising, though, but somehow expected, I mean, my friend Michel Armand was always telling me that with sodium, you can always get better ionic conductivities in this system. And actually, he was right, because with the composition I just described, we get pretty good conductivities at room temperature, about a millisiemens per centimeter, but we still have decent conductivity at minus 20 degrees centigrade, okay? And since anyway we want to employ it in seawater batteries, then the temperature of the battery is going to be fixed by the temperature of seawater, and the coldest liquid seawater you can find is about 4 degrees centigrade. Okay, so but in most of the cases it's a little bit warmer. But anyway, even assuming 4 degrees centigrade, we still have conductivities of the polymer electrolyte, which is in the order somewhere between 0.5 and 0.80 and 0.8 millisiemens per centimeter. Transference number, obviously in this polymer electrolyte, we have several mobile species, not only the lithium, the sodium, but also the anion, FSI, as well as the ionic liquid cation. So we don't expect to have a very high sodium ion transference number. Nonetheless, applying the famous method of Bruce and Vincent, which can give you an indication. So I would not put my right hand on the fire on this number, but we get something which is in the range of a transference number in the range of 0.2, which is, however, twice as much the the one you would get if you do exactly the same experiment with the lithium FSI instead of sodium FSI. So definitely sodium ion can really move better into the PO matrix, confirming what Michel Armand has been telling me since many years. Okay, electrochemical stability window. This is very important. We want to be able, I show you that the cell needs to go to high potential. So we want to be able to plate sodium, and we can do it. Okay, there is no problem. Consider that these measurements are done against the copper foil for the cathodic and the steel foil for the anodic measurement. Okay, so there we are actually, this bump you see here, it is actually not the composition of the electrolyte, but is the decomposition of the oxide on the copper foil, okay, which is decomposing by reaction with sodium. On the right, you can see the sodium plating and stripping in anode-free configuration. So there was no sodium in this cell, okay? It was a current collector and the polymer electrolyte I described before. Okay, so we can really plate and strip sodium over the current collector rather than starting from sodium. Okay, the limiting current density, we also did this determination. We just made a sodium cell with a polymer electrolyte in the middle, and then we start to polarize with 0.1 milliampere per centimeter square, and you see that we have a pretty reversible curve. However, when we go to 0.2 milliampere per square centimeter, then we start to develop dendrites. So the limiting current is somewhere between 0.1 and 0.2 milliampere per square centimeter. But obviously, we did not only test the electrolyte, but we actually tested the functionality of the concept. Okay, so we made a sodium seawater cell with the Nazigon. This is the Nazigon electrolyte, preventing water from reaching the anodic compartment, the polymer electrolyte, and the current collector, which can be either aluminum or copper. There is not much of a difference. This is the cell structure. On the seawater side, we use carbon felt, no catalyst. Okay, and as it's shown here, we can get actually 30 charge-discharge cycles. Oh, actually 25, let me correct. For sure, this is 25 we have on the graph, okay? And the process is pretty reversible. Here, we limited the capacity to 1 milliampere hour per square centimeter, but we get a round-trip energy efficiency of about 94%. I mean, this is definitely a promising value, which is of definite interest for the electricity. On here on this graph here, what you see is actually the prolonged sodium plating, and this is for another kind of application which I will describe a little bit later. But we actually wanted to test what happens if we start to deposit a large amount of sodium metal at the anode, and you see that there is not much of a difference. There is a polarization occurring in the polymer, but there is no practical limitation. You can go forever. Okay, why were we interested in this large amount and also in other approaches? Here is a little bit more complicated sodium seawater cell. Still, we have the seawater compartment here. We have the Nazigon to prevent seawater to get in contact with the anode, the negative electrode compartment. But here, what we have two negative electrodes. Okay, here we have a grid that is actually favoring the reaction between the sodium ions that are coming out of the sodium with the biphenyl, 2,4 and 1 electron, which is collected by this anodic grid, to form sodium biphenyl, which is let's say a carrier of metallic sodium and is soluble in the electrolyte we are using. And this is for practically a kind of redox flow cell concept, okay? Because the sodium biphenyl solution can actually be pumped out of the cell and accumulated in another container, or can be subjected to a further reduction to produce sodium metal, which then can be accumulated forever in appropriate containers and stored there, okay? And this is actually a project that has been funded by the Italian Ministry of Technological Development. I don't remember now, because they just changed the name. And sees involved the University of Rome as well as the University of Perugia. Okay, these are the demonstrations of the concept, okay, that we did in the past. And again, you see here, this is the first step in which we actually are generating the sodium biphenyl. You see the voltage is a little bit lower. This is a full cell, sorry, I did not want to do this. This is a full cell, a full sodium seawater cell. And at the beginning, what we are forming is the sodium biphenyl. And once the sodium biphenyl is saturated, then we start to have the sodium metal plating. And we can go kind of forever. And chlorine production and water desalinization, these have been demonstrated. And obviously, we can also do the opposite during discharge. So now we have sodium metal, and we can actually achieve aerial capacities of like more than 40 milliampere per milliampere hour per square centimeter. But if we flow the electrolyte, this cell can go forever. And again, so in addition to the stationary storage, this cell can also be very useful for marine transportation and onshore, offshore power generation, okay? Because you only need a lot of seawater available for the reaction. Okay, so overall, the sodium is also a very interesting energy carrier and storage. It offers about 3-4 times the volumetric energy storage of liquid hydrogen, but it also promises very high round-trip efficiencies. Okay, in our cells, we have demonstrated about 85, even more percent in the very last results. Okay. And as I mentioned before, you also get chlorine, desalinized water, and sodium hydroxide for CO2 trapping. Based on this preliminary experiment, we designed a business case for Sardinia. Sardinia is a beautiful island in Italy, which I do not want to cover with photovoltaic panels. It's too nice to be covered with photovoltaic panels. It was just an example that I made at the beginning, okay? It has some strange energy characteristics, though. It's not connected to the natural gas network, which is everywhere in Italy. It has a kind of old energy infrastructure because the old infrastructure in Sardinia was made in the 60s, 70s of last century. So presently it's a little bit old and needs to be anyway renewable, and also it has anyway great renewables potential. Not photovoltaic panels, but there is plenty of wind onshore and offshore, and there is and also wave energy is available. Okay, the primary annual energy needs of Sardinia is about 23.5 terawatt-hour, which is not that much. And in order to cover the storage need for the season, we only need to store about 4.5 terawatt-hour. I remember these are 4.5 soccer fields. I recall 4.5 soccer fields covered with 7 meters of aluminum. I'm sure there are hundreds, thousands soccer fields in Sardinia. Okay, so to produce the energy for Sardinia, we only need 69 square kilometers of photovoltaic panels. I'm not considering wind energy, wave energy. I'm only talking about photovoltaics. Okay, and this is the comparison we get out. Okay, if we use sodium, we need much less space than if we use hydrogen, for example. Okay, so the use of the seawater battery would allow much higher volumetric energy density and much higher energy efficiency. We estimate at least 70% based on the lab results we already have. And then, as I mentioned before, we have this chlorine production. Maybe a lot of you doesn't like it, but I can tell you that especially during the COVID time, with the production of disinfectant and so on, I mean, the chlorine usage has grown crazy. We produce a lot of desalinized water when we are actually in summer, when we are actually accumulating energy, which is very good because Sardinia in summer is full of tourists and they really need a lot of water, which they don't have available. Okay, so producing in situ desalinized water would be a perfect case. So we would produce about water for about 1.6 million inhabitants, to give you an idea of the numbers. Okay, as well as we would trap about 58,000 tons of CO2 per year. Okay, which is also pretty good. So in summary, my presentation, I just want to stress that sodium and other abundant metal-based energy system can help addressing the problems associated to the energy transition, okay? In the sustainable transportation, definitely, okay, sodium-ion battery can be used for scooters, light-duty vehicles, and so on. I didn't talk about this very much today. Definitely, they can also, the sodium seawater batteries can be used for marine transportation, but also for the delocalized power generation for the EV charging infrastructure. I mean, we have to deploy a charging infrastructure everywhere in all Europe to charge our vehicles, but the grids we have are not designed for this. So rather than changing or making completely new grids, it would be wiser to use an energy carrier like aluminum or sodium and supply this to the charging station and then produce the electricity and the hydrogen in situ, okay? And in fact, this is also, and then related to this, the seasonal energy storage, which the market perspectives here are really huge, okay? Stationary storage, sodium seawater batteries, also sodium-ion batteries, but definitely for the seasonal annual electrochemical, this is where we really need a lot of energy storage to be sure that we are not going to have problems next winter, okay? And this is very important. So that's my presentation. Most of the work I presented, actually, I would say all the work I presented was actually done in HIU, which was my former institution till 19 days ago. And then also the funding agencies, the German funding agencies, but also the European agency. Professor Barelli for the collaboration. And if I can have 2 more minutes, I'm still coordinating this European project, which is called STORIES. It's about 7 million euro funding, and is a storage research infrastructure ecosystem. So the partners, the members of this project do not get any funding. The majority of the funding goes to the infrastructure providers. And we are talking about world-class infrastructures in Europe. And they are going to support scientists that make use of these 64 infrastructures which are made available by the partners as well as the beneficiaries of STORIES. And we are just about, we have a second transnational access call open. So if you have interest, take a look at the website of STORIES. You can really find this top of the world, world-class infrastructures available for any kind of research. Is not only batteries, okay? It can be thermal storage, chemical storage, mechanical storage, so pumped hydro or flying wheels and so on, okay? And if you want, you can apply you can apply a proposal and then get funded to spend time in this infrastructure and get results. With this, I think I can close my presentation because, as usual, I'm sure I exceeded my time. Thank you for your attention.